Okay, and good morning, and we shall continue with our next lecture, lecture number 7, etching and materials removal. So, as part of the process of microfabrication, uh, we know that the process begins with the preparation of materials, and then we look into deposition, and uh, should the design required of removal of certain materials, there will be certain process that we can do in order to get the structure of the materials or the structure of the design to be formed. So the forming of this certain structure, certain design, certain shape of the design is done by etching. For example, that is the most common process in terms of removing the materials from silicon substrate or any other substrate of the device. So what we're going to look today is the etching overview and some basic terminology. Then we have a wet etching and dry plasma etching in terms of mechanism, example of reactor design, and then a summary of the process of etching and materials removal. So what is etching in terms of definition? So etching is a microfabrication process that selectively removes materials from the surface of a wafer to create intricate patterns. So here the keyword here is selectively remove. So in design of microfabrication, micro devices, we know that we want to form certain structure, certain pattern. So, and there must be selectivity in terms of removal. So in the case of using machining process, conventional machining process, we have machine tools in order to do the milling, for example, grinding. So there is no need for selectivity. So, but in this chemical process or reaction process, the selectivity will be very critical in terms of the process to form the pattern. It is a critical step in manufacturing semiconductor devices and microelectromechanical systems. The two primary types of etching are wet etching and dry etching. So these are the two types of etching. What is wet etching? So wet etching uses a liquid chemical solution called an etchant to remove unwanted material or to form a certain structure, certain pattern. The wafer is submerged in the etchant, which react with the dissolve the materials not protected by mask. So that is where you have selectivity. Selectivity, if you have mask, meaning the mask won't be removed or won't be dissolved by the etchant. So the etchant will only remove the required part to be removed. For example, if you want to remove certain silicon material, or you want to remove certain silicon dioxide, for example, or anything related, or I mean, sometimes we remove the polymer materials as well. So with some protected mask. And what is dry etching? So dry etching is or plasma etching uses a gas phase process where a plasma of reactive gases and ions remove materials. So with a dry etching, so you kind of use gas ions to remove the material. So the charged particles are accelerated towards the wafer, etching the exposed areas. So in this case, selectivity also happen where some materials can be removed quickly. Some materials might be able to withstand the bombardment of the ion or the reactive gases. So the exposed areas, meaning is not covered by mass, so then it can be removed. The material can be removed accordingly. So the key characteristic mechanism of wet etching is a chemical corrosion. Basically, it's a corrosive process, and immersion in a chemical bath or spray. Basically, you have the bath of the chemical or the liquid you spray on the material on the surface to the material, then it can corrosion happen, then it's remove the material. It's an anisotropic process, generally isotropic, meaning it remove material equally in all direction, creating rounded or undercut features. An exception is an isotropic wet etching of crystalline material like silicon, which etch faster along specific crystal plane. So if the material is not a silicon, for example, it will remove in all direction. But we know that silicon has a crystal direction, even though it's not attack in certain direction, but it still will have the effect. But the rate is might be different in certain orientation of the crystal. Meaning to say that for silicon is much easier for us to use wet etching to form certain shape if we use with certain direction of the crystal alignment. So selectivity can be highly selective as different etchants react with specific materials. So the keyword for the removal of wet etching and also dry etching as well is the selectivity. So we know that certain materials, certain chemical will react with some other materials. So, and the rate what might be different. It can be different when we have different concentration, for example, of the chemical, and also with different reaction with the material. And cost and speed uses simpler and less expensive equipment and is often faster for batch processing. So we know that in the semiconductor process and as well as in MEMS, batch processing is very important for us in order to reduce the cost. So using wet etching is quite desirable. Drawbacks: less precise than dry etching, involve the handling of hazardous chemical and generate liquid waste. So basically, in order to avoid contamination, for example, the chemical can only be used once or twice, then we have to replace with a new chemical. And also that will become waste, liquid waste, and the chemical used always hazardous, such as hydrochloric, sulfuric acid, etc. So, and in dry etching, what is dry etching? In terms of mechanism, a combination of physical and chemical process. So energetic ions physically dislodge atoms, while reactive radicals chemically react with the material to form volatile compounds. So highly anisotropic, allowing the precise control and the creation of vertical sidewalls and high aspect ratio features. So in comparison with the wet etching, dry etching can form a high aspect ratio structure because dry etching is more directional. It can be directed to a certain direction so that you can remove the material according to the direction. It's don't, I mean, in a way, it's just attack where the direction of the ion is directed. In comparison with wet etching, you just submerge the material, and the material, the chemical will fill everywhere, and it will attack all direction without any specific direction. So cost and speed requires complex and expensive equipment and typically has lower throughput for batch processing. And the drawbacks can cause surface damage from ion bombardment, and achieving high selectivity can be more complex. So because it's a quite kind of forced process machining, where the bombardment of ion with force and speed basically can remove the material, even though the selectivity might be a part of it, but somehow continuous bombardment of ion can also remove the material. So that is where the surface also need to be taken care of. So other material removal process technique used for removal, machining, mechanical machining. And at a certain extent, we can still use machining for some bulk process. Let's say dicing. We need to dice the wafer after the completion of the process. For example, dicing is just using diamond cutter. Then we can use the micro milling, for example, for bulk removal, and we can use abrasive tooling for removal of forming of surface of the material, etc. And chemical and mechanical planarization, CMP, this process combine a chemical slurry with a mechanical abrasion from a polishing pad to create an exceptionally flat surface. It is used to smooth surface wafer between fabrication step. So normally when we process the silicon wafer, we go through certain process, and sometimes we need to kind of make it flat again with this kind of CMP process. And with some other materials as well, there are sometimes you need to do polishing, etc., in order to get a good surface roughness of some other materials. Then we have a laser beam machining. A high energy laser melts and vaporizes material to cut or drill holes. So in certain cases, we might need to have a certain structure of the wafer or the substrate. Then we can also do with a laser beam. So laser beam also with the micrometer or nanometer spot of the beam, we can have a microstructure to be formed. Then we have electrochemical machining, ECM, a non-traditional process that uses electrochemical principle to remove material without mechanical force from a conductive workpiece, often described as reverse electroplating. In previous lecture, we have looked into electrodeposition. So the reverse use of electrodeposition, I mean, we know that one side will be removed and one side will be deposition. So in a way, it can be a removal of materials as well. I mean, etching or removal of material on the anode side of the setup of electroplating or electrodeposition. Okay, and for etching of thin films and sometimes the silicon substrate are very common process steps. Usually selectivity and directionality are the first order issues. So in this case, in this example, if we want to form this kind of shape, in this kind of pattern, we need to have a mask. Then we need to cover this part basically initially. Then we want to remove this part. So what we can do is deposit a thin film of let's say here maybe silicon dioxide or some other metals material, for example. It can be a metal or anything. And with photoresist, we form the pattern. Photoresist will act as a mask. Then with this mask, you expose the photoresist exposure, then you get the mask. First, you etch you develop the photoresist in this pattern. Then now the etching process. The etching is the removal of this part. Okay, this part. So using certain chemical. If it's metal, for example, you want to have a circuit on this substrate. Then if it's gold, you might use gold etchant or some. I mean, it depends on the materials. Then later on, once it's formed, this is, I mean, if you see in this case, you might see that it's quite straight. In actual, it might have certain different pattern, not that straight. But I mean, that is quite normal in the formation of using wet etching, but this is, I mean, etching in general. Then we can have this, after we remove the resist here, we can have the structure. So this is an example of after removal of the material here, you can have this pattern on the substrate itself. So the thing is, what happened, I mean, what is, I mean, how we can control etch rate, selectivity, anisotropic, and uniformity. So the etching rate, the etch rate here is a speed at which etching occurs. So how fast you can remove the material that you want to form the pattern. That is what we call as etching rate or etch rate. And selectivity is a ratio of 2 etch rate. So for example, you have one material with an etching rate of R1 and certain material, some other material with etching rate of R2. So now, let's say here in this case of silicon dioxide, etching with a hydrofluoric acid. Okay, so you know that a hydrofluoric acid will etch the silicon dioxide. So determine the etch right time for 1 to 2 micrometer thick silicon dioxide film, which are equal 400 nano per minute. So you can do within 3 minutes, basically 400 nano, 1.2 micron. How thick should the resist must be if the selectivity is 4? So SiO2 over resist is 4. So the etch rate and selectivity are crucial for defining the photomask. So here we can calculate if the selectivity here, R1 divided by R2 is 4. So you know that R2 will be, with this value, you can calculate the R2. So that is where you know how thick you have to prepare for the resist in order for you to have the material can withstand the etching rate of the a few minutes in order for the 3 minutes of etching 1.2 micron, then how thick will be your resist. So the photoresist need to be thick enough in order for you to protect the covered, the masking area. So this is another what happened to the mask and what happened to material removal. So isotropic etching remove material equally in all directions. So undercut of the mask. So we have the mask here, photoresist, for example, or it can be some other materials as well. I mean, depends on the process step itself. So because of the chemical will go in, I mean, firstly it will attack here on the surface area, but of course once it go here, so all direction of this SiO2 will be attacked, will be etched by the material. So from here onwards, it will go here, go all direction. So that's why undercut happen. So meaning to say, if you have this size of distance of, for example, 50 micrometer or 10 micrometer, here it might go undercut of a few micrometer to the side. So this, I mean, it can be consideration during the design process. If you consider that the thickness is at certain thickness, you want to remove the material, then the undercut happen, then you might be able to calculate it in advance. If you dip into the wet etching process for a few minutes, for example, then you will get undercut. Then by default, your design has to consider this, and you might want to make this opening is little bit smaller to consider the structure that you want to remain might be have undercut later on. So that is kind of the strategy that we can have in advance before we do the process or at the design stage. So that is one thing. Then anisotropic etching remove material only perpendicular to the surface. In this case, this is anisotropic. This is isotropic process. So accurate transfer of the mass pattern. So for anisotropic, vertical edge minus horizontal edge rate divided by vertical edge rate will be something that you can consider in terms of the how wide it will be edge. So uniformity and or homogeneity measures the distribution of the edge rate wafer to wafer, especially for multi-wafer processing, and across one wafer, example center versus edge. At the center, it might be different. At the edge, it might be a different edge rate. Has to be considered when determining etching time. So you want to prevent over etching. And for production, matching production tools, especially lithography and etching. So here we can see that some simulation you can do. So etching performance basically defined by what we have mentioned, the etching rate, R, the film thickness being etched per unit time. R has significant effect on the throughput. So how fast you can etch will determine how fast you can produce the device itself. So edge uniformity, variation of edge rate throughout one wafer, multiple wafers or multiple batches of wafers. So uniformity might differ if you have a spray wet etching process, for example, or you have a dry etching process where the position that you put the wafer or the sample might have the effect of the etching. So at the center, for example, of the using a dry etching, you might get a good etching rate as intended, but at the edge of the wafer, you might have a lower etching rate. It's the same as goes with a spray etching. In the wet etching process, if you are using spray, then the etching rate at the edge of the, which is far away from the spray nozzle, it might have a lower etching rate. So selectivity, the ratio of the etch rates between two different materials. So as mentioned, if different materials have a different etching rate, but you have to cater the process time as well, because etching with the etching rate, you know that a certain material will be etched faster in comparison with some other materials. But if you use as a mask, for example, the mask has to withstand certain time as well in order for you to have a different thickness to be etched, to be removed. Because we know that the mask normally is not as thick as the material that you're going to remove in the case of you are patterning silicon. You want to remove, for example, in the case of wafer silicon, up to a few micrometer, maybe 15 micrometer, or even 80 or 100 micrometer, then with a thickness of a polymer on top of your, as a mask, maybe a few micron only, a few, maybe 10 of micron for the masking. So that will have, to be considered at the beginning of the process in terms of the selectivity of the etching rate. And isotropic etching directionality, whether it's an isotropic process or anisotropic process, you have to consider from the beginning of the, let's say in the case of undercut that we have mentioned just now, if undercut happen, then what will be the mitigation process. So this is what we have mentioned just now. So pattern transfer, lithography plus etching. So normally we have lithography to form this kind of, this is a pattern. Then this is undercut that we have shown before. So you see that the intended size of the structure here is as this mask, but due to undercut of wet etching, For example, you have a smaller structure to be formed here, and the material has been removed because of isotropic process. The chemical kind of attack in this area and is formed this kind of narrow shape. And in this pattern, in this process of lithography, you have your photoresist here, then this kind of photography is formed if you do wet etching, is also remove this pattern actually. So that is the selectivity of this removal of materials then that affect the etching process. So directionality. So here, I mean, as explained before, if it's isotropic, then you have the attack on the side of the material, which form is not non-straight structure. So if it's more directional, meaning to say if you are in maybe dry etching, using dry etching, for example, or the etching with a certain control process, you have a kind of directional of removal. You can, if A equal 1, then you can have a straight pattern, no undercut, for example. But you can actually calculate this assuming S equal infinity in this case. So this B overhanging of this or undercut here can be calculated according to this. Then with the etching rate here, you know that how much material will be removed as the undercut due to time of etching. So in wet etching, what we are using, for example, to remove silicon materials, we use nitric acid and hydrofluoric acid. This is a quite common materials, common chemical, hydrofluoric and nitric acid. And also for etch of silicon nitride, we use hexafluorosilicic acid, for example. So these are a quite common isotropic process of chemical etching for wet etching for the silicon. So another example, I mean, of the etching, because we know that silicon has a crystal orientation. So this kind of cutting is possible. So anisotropic wet etching result from surface orientation. I mean, we know the cutting of the wafer in what direction of the crystal, then we can manipulate that in order to get certain shape of the structure for the wafer. So this is a wafer orientation, crystal orientation. So 100, 110, and 111. So due to this orientation structure, you know that the etching rate of the Si, the silicon, will be different. So you can attack in the surface of certain orientation and less, there is selectivity for the orientation of the crystal. For example, you can have this kind of structure, 111 surface here. So if you have exposed, has a mass here, then with this surface opening of the crystal orientation, crystal surface, then you can have this kind of shape with wet etching. Okay, this kind of surface of tapered silicon surface. And wet etching application. So you can see that these are the example of microstructure that can be formed using etching. So removal of materials from the surface. So this kind of form. So everything using etching, maybe wet etching or dry etching, and overhanging structure. But of course, the process might be complicated, and it's not just one pass process, but a few steps process that to form this kind of structural, what we call as a cantilever beam, etc. So the drawbacks of wet etching: in the manufacture of a large-scale electronics integrated circuits, wet etching is being replaced by dry etching, basically. Wet etching is mostly isotropic, meaning to say it's a take all direction. And wet etching has poor resolution because it's not that controllable in terms of process. And wet etching depends on a lot of corrosive chemical, which are harmful to human bodies and environment. So we have to wear PPE for the process of in the clean room, basically. Wet etching needs a large number of chemical reagent to wash away the residues. Is considered not economically. So at nanoscale, the requirement of etching is, we know that we're going to become more and more smaller structure to be formed in order to have more sensitive performance, higher performance. For example, here the etch requirement at the nanoscale to obtain desired profile with certain shape, 150 nanometer of a polysilicon structure in this way. So a minimal undercutting or bias, we want to have a direct cut, not undercutting, because if you want to have a high aspect ratio, 150 nano in comparison with this side of 50 nano, which is this is 3 times bigger than this. So if undercut happen, so this all will be removed. So you cannot get this kind of high aspect ratio substrate or structure for the nanoscale using wet etching. And selectivity to other exposed film and resist is also a concern. Uniform and reproducibility, minimal damage to surface and circuit, and a clean and economical and safe. So this might be the things that need to be considered for the nanoscale process. Maybe if we still use wet etching, the thing, it might be not possible to get all these things. So therefore, we will look into the next process, which is the plasma or the dry etching process. So in the plasma process, you have, this is what we call as plasma. You know, the state of the material, you have solid, liquid, and gases, and the fourth states of the material is called plasma. So yeah, it's arguable. Maybe some certain people do not agree with the term of plasma, but in terms of here, we can use the terminology as far as it work for us. So in the solid state, basically atoms and molecules are fixed in the crystal lattice. In the liquid state, atoms and molecules can move freely as a network. And in gaseous state, atoms or molecules can move freely in large distances. In plasma state, ions and electrons not bound a very large distance. So it can go anywhere, basically. So the plasma generation, so in order to use plasma etching, we have to generate plasma. Application relevant generation of plasma in parallel plate conductor. So you have electrode, 2 electrode, then you have a plasma shed here. Then you can form plasma using RF, basically, radio frequency power input. So you have a ground here, and you have a gas inlet such as argon, CF4, or O2, oxygen. Then you get gas outlet. So what happened is anode is grounded, cathode connected to RF generator via impedance matching network. Then high electric field ionized gas molecule, and you form plasma. You generate plasma by electric field that ionize the gas molecule. Fast electron follow RF field positive ion determine plasma potential. So a smaller electrode leads to a higher voltage difference compared to a plasma. So you can see here, you have a voltage and the electrode target. Then this is the electrode, the other electrode. So positive electrode equal to equal area electrode here. Then this is the distance between two electrode. So the unequal area of electrode here is smaller electrode at the left. So that is where you can set up of the plasma generation. So high energy electron in a plasma lead to further reaction. So because plasma move in high energy, so it can form etching as well. So it's kind of bombardment. You are shooting ion to the materials to remove. It's a force machining. It can be considered as force machining as well. So for example, you have CF3 plus F plus electron here. So this is a disassociation process. Then with this association, you have ionization of CF3. Then you have this ion will be bombarded to the substrate in order to have a physical etching. And this side is on the chemical etching process. Okay, this association is a partitioning a molecule into components. It creates a free radicals basically, and ionization is a further generation of free electron and charged molecules. So excitation happen, excited molecules relax and emit photons. That is where you can see the glow, and recombination radicals and molecule recombines. So in plasma etching, typically there are about 10 to the power of 15 cubic per cubic centimeter neutral species, 1 to 10% of which may be free radicals, and 10 to the power of 8 to 10 to the power of 12 cubic centimeter ions and electron. In standard plasma system, the plasma density are closely coupled to the ion energy, increasing the power, increase both. So there are three principal mechanisms. One is a chemical etching, isotropic and selective. And the next is a physical etching, anisotropic and less selective. So this physical etching is considered as a force. Okay, ion enhancement, ion enhanced etching, and isotropic and selective. Most applications today try to use ion enhanced mechanism, which provide a better removal of the material, which you can have a straight cut, for example, of the material. Okay, this is you can see the process, the chemical etching. So you have your etchant, free radical creation. So you bombard the etchant here, so absorbed by the surface, at the surface, then it remove the material. So this is the mask, must have a different selectivity. So the film or the substrate that you want to remove. So for example, the removal of your, so the process will be quite slow, but somehow you can control the process due to certain recipe, whether it's aggressive or a slow process. So both process of physical and chemical etching happen. So this case is about chemical etching. So this is the equation of the process in terms of chemical etching. And in plasma etching, as mentioned, you have two, chemical etching and physical etching, or we call it a sputter etching because you bombard the ion of the gas that remove the material. So purely physical etching and highly directional, meaning to say is the direction of the bombardment of the ion will be the material removal area. or location. So etch almost anything. So even though you have this kind of uh, selectivity of different materials, so but somehow it will etch as well because it's about force removal of the materials. So the rate might be different, but somehow the removal happen. And poor selectivity, all materials sputter at about the same rate. And pure sputter etching uses argon damage to wafer surface and device can occur. So for example, a trenching ion and bombardment damage, radiation damage, and redeposition of photoresist and charging. Redeposition of photoresist meaning here, you see that you have photoresist, but this photoresist also being etched by the bombardment of the ion, then is redeposit on the other surface, which is exposed. Then a charging here. So if a charging happen, then the direction of the ion will be not straight. So you will have this kind of undercut, for example, because of this charging of the surface here. It will, because this is positive charge ion, then because of the charging, let's say this is also, this is a negative, so it will attract the positive charge to be slightly bending to the side. So this will cause the different, not straight cut to the materials removal. So these damages can occur in any etch system with a dominant physical etching component. So ion enhanced etching or reactive ion etching, this is a quite versatile equipment basically process, which reactive ion etching is quite a complex process that can provide a good shape of geometry of the pattern. It has been observed that chemical and physical components of plasma etching do not always act independently, both in terms of net etch rate and in the resulting etch profile. So you see that you have HF gas of etching and argon ion beam etching, then argon ion beam only. So these three profiles might be combined, for example. So etch rate of silicon as XeF2 gas, not plasma, and argon ion are introduced to silicon surface. Only when both are present does appreciable etching occur. Etch profile can be very anisotropic and selectivity can be good. And many different mechanisms proposed for this synergistic etching between physical and chemical components. Two mechanisms are shown below here. So you have a different mechanism here. So you have ionic species to etch the materials. Then you have reactive neutral species, which will, cover up here inhibitor. Then you can continue for the etching of this material. So chemical etch enhanced by ion bombardment, but here inhibitor removed by ion bombardment. So ion bombardment can enhance etch process, such as by damaging the surface to increase reaction or by removing the etch byproduct. So ion bombardment can remove inhibitor, that is an indirect byproduct of etching process. So the removal of this, you have the maybe the material removed remain somewhere on the surface as well. So that is why ion bombardment can remove inhibitor that is indirect byproduct of the etch process, such as polymer formation from carbon in gas or from photoresist itself. So whatever the exact mechanism, whether it's multiple mechanism may occur at the same time, need both components for etching to occur. So whether it's a chemical etching or physical etching, and get an isotropic etching and little undercutting because of directed ion flux. So it's a kind of straight movement of the ion, and get selectivity due to chemical component and chemical reaction as well. So in this case, reactive ion etching, there are many applications today to fabricate good structural shape of the design. So in summary, for plasma etching mechanism, we can have the SE sputter etching. This is with a certain orientation of the crystal. So this is a plasma etching, PE, physical. So the directional of the ion might work, but somehow the undercut can happen because of a chemical process. This is a sputtering, this is a chemical. So reactive ion etching, so with a control of the process, you can have a kind of straight cut in this way. So that is very good. And the reactive ion etching, deep RIE, basically you can have a inhibitor which cover the side, then you keep removing material at the center of the process where it can be a straight cut later on. So that is kind of slightly the different approach in terms of plasma etching in order to have a good cutting of a material removal according to dimension that required. So an example of reactive ion etching, you can see that with a photomask, the inhibitor covered the surface. Then once etching happen, then it can be a straight cut edge final profile in this way. So highly selective silicon etch process, the goal is for MOSFET, for example, you want to have a good shape of the material in this design, but the requirement is to have a high aspect ratio of structure. Polysilicon with 100 nano with this is as maybe less than 30 nanometer of this. Then if the process is just a normal wet etching, you might not get this kind of straight structure because of under attack of the side wall. So in deep RIE, so it's quite possible to make it a good structure in this way. For example, you use an anisotropic HBr02 RIE process. So you have a polysilicon, then you have high aspect ratio. This is 3 nanometer, and the height is 102 nano. So 26 nano here. So it's quite high aspect ratio process can be formed in the use of deep RIE. And the design of the reactor, different configuration can be, I mean, you can see a few different configuration of the reactor. This is kind of a typical barrel etchers, purely chemical etching. So you have your wafer inside, then you have your plasma shield, then you have a gas inlet here. Then with that you can do the etching. Okay. So parallel plate system. So this is what I've shown before. So then you have in summary the plasma etching. What we have discussed is it can be controlled in order for you to have a straight etching process by avoiding the undercutting to happen using chemical etching. For example, because you can control the bombardment of the ion and to have inhibitor in the side wall to be deposited over time while the process is happening. So the control of the inhibitor process and the bombardment alternately over time with inhibitor become thinner, then you deposit again the inhibitor with the bombardment of this ion to remove the straight path can be performed. So in summary, for etching, what pattern transfer can be done from lithography and etching. Then what is important is on the selectivity of the material, whether you can have a material to be undercut or straight cut, etc., to form a good structural geometry is depend on the process of using what process you are using and what material for the masking to be the to be used as a different in terms of different selectivity. And wet etching happen with isotropic and anisotropic process is also happen. It depend on the, if it's about silicon, it depend on the orientation of the crystal structure. And for dry etching, only physical etching like sputtering and reactive ion etching, basically this directionality and selectivity improvement using CF4O2, and only chemical etching for physical etching. So for the etching of thin film is a key technology in modern IC manufacturing, and photoresist is generally used as a mask, but sometimes other thin film also act as a mask. For example, you can use silicon dioxide as well. Selectivity and directionality are two most important issues. Usually good selectivity and vertical profiles are desirable, and we want to have a good selectivity and directionality in order to have a geometry as intended. And other related issues include mask erosion, edge bias, undercutting, for example, and edge uniformity, residue removal and damage to underlying structures. And dry etching is used almost exclusively today because of the control, flexibility, reproducibility, and anisotropy that it provides. And physical reactive neutral species, free radical and ionic species play roles in etching. And generally, neutral species produce isotropic etching and ionic species produce anisotropic etching. So this is a kind of common action for etching. For polysilicon, you use this kind of etchant, and single crystal, some of the etchant and polysilicon, and silicon dioxide, this etchant, etc. So you can always refer to the etchant kind of the textbook. That's all. Thank you. Any question from the floor?
Sir, hello, sir. How can we easily itching depth? Itching depth. Easily control the itching depth. Depth.
Okay. Etching depth. Etching depth is controlled by the time and also the if you talk about dry etching, I mean wet etching. If you talk about wet etching, is a time and also the concentration of the chemical.
Main parameters is time.
Time
Time
yes,
dependent.
Time dependent.
Okay, sir.
Yeah.
Okay. Thanks.
Thank you. Okay, thank you very much.